Hello, physics students. This section today is called power. And what do you think of when you think of power? There are a lot of different things you might think of. You might think of how power is transferred to us from power plants. You might think of the power button on your electronic device. You might think, I have the power, ha 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 ha, right? Or power as in very strong and powerful. Who knows I don't know what you think of. But we're going to learn what power is when we talk about power in science. It has a very specific definition. We're going to look at how we can calculate power, and we're going to look at a few examples of how to calculate power. In physics, power is the rate of energy transfer. So it's how fast is energy being transferred. And the formula for power is work divided by the change in time. So when we think of power, power is going to be in a new unit, watts. Work is, remember, in joules. It's the amount of energy that's being transferred. And time, obviously, is the rate, the amount of time, and we measure that in seconds. We have to have work in joules and time in seconds in order for power to be in watts. So if we start with this equation, that power is equal to work divided by the change in time. It's the amount of work done per time. We can actually come up with an alternative equation very, very simply because we know what work is. Work is equal to force through a distance, right? Force times distance, and we keep our change in time. We also know that distance over change in time is equal to velocity. So if we simply substitute velocity in for this portion of the equation, we get power equal to force times velocity. And this is just rewritten down here, an alternative equation, power equals force times velocity. Obviously, you can easily derive this equation as well. Let's look at the units for power and review a little bit about units. We know the SI unit for power is the watt, and it's abbreviated capital W, not to be confused with the variable for work. 1 watt, we know, is equal to a joule per second, and that's easy to remember because power is equal to work divided by time, and the work portion is in joules and the time portion is in seconds. So a joule per second is a watt. Just to review, remember what a joule is. You remember your formula, work equals force through a distance. Well, our force is in newtons. The displacement is in meters. So a newton meter is also a joule because work is in joules. If you break that down further, force equals mass times acceleration. Mass is in kilograms and our acceleration is in meters per second squared. And if we substitute values in there, we have kilogram meters per second squared, and then when we multiply by distance again, we have another meter we're multiplying it by. So it's kilogram meter squared per second squared. That is also a joule if you take all those individual units. So just this is to help you keep track of these in your brain. A newton is a kilogram meter per second squared. That's what we measure force in. Mass times acceleration would be the kilogram, and meter per second squared, that is a newton. That's just a little review for you. Also, FYI, and you might need this in your lab, HP stands for horsepower. That is not an SI unit, but if you want to convert watts into horsepower, here is the conversion unit for that. 1 horsepower equals 746 watts. So one way that we can think about power, remember, power is the amount of work done per time. If you have different power ratings for different machines, those differences in power ratings do not mean that a different amount of work is done. It just means that it does the same amount of work but in different time intervals. And a little example for that would be if we compare different motors. These different motors are going to give us different power ratings in kilowatts for these examples. They do the same amount of work, but this motor is going to do the work slower in a different amount of time. Let's do a little example just to illustrate that. Let's say that we have a curtain that needs to be lifted, and we have a little curtain motor, or we want to find a curtain motor. And we have some different power ratings for different curtain motors. And here are our specifications. We'd like to know which curtain motor is going to apply the best to our situation. And in our situation, we have a 193 kilogram curtain, and we want to raise it 7.5 meters, and we want the speed to be as close to 5.0 seconds as possible. So let's set this problem up. We know the mass of our curtain, we know the time that we want this to be happening in, we know the displacement that the curtain, that this motor is going to need to take the curtain, how far it needs to raise it. We want to find the power that we are requiring for our little motor. So we know that our equation for power is power equals the work divided by the change in time. We can substitute force times distance for the work over change in time. We can also substitute for force. We know that the force at work against the motor, against which the motor is going to be raising this curtain, is going to be equal to mg. It's the force of gravity. And then we keep our the distance included in the equation. So all we did here was substitute for force the m times g. We still have our change in time. Now when we plug values in for all of these, we get, there are the values all substituted in, 193 kilograms for the mass, 9.81 for g, and 7.5 for the distance, 5.0 seconds for the change in time. I get 2.8 times 10 to the third watts, which is also simply 2.8 kilowatts. And that is closest to the 3.5 kilowatt motor. If I were to choose the 1 kilowatt motor, it would lift the curtain very, very slowly. It would do the same amount of work, but lift very slowly, would perform it in a different amount of time. And this motor will lift the curtain too fast. So this would be the one that I would end up choosing because it's closest to the amount of power that I'm requiring. So let's look at another example. Let's say 2 horses are pulling a cart, and each horse exerts a force of 250.0 newtons, and they're going a speed of 2.0 meters per second, and they travel for 10.0 minutes. How much work is done by that is a typo, it should say 2 horses, not tow horses. How much power is delivered by the horses? So if we have our horses both traveling in the same direction, we know that the force is going to be, they're both going in the same direction, parallel to each other. We know the force is going to be equal to 250.0 newtons plus 250.0 newtons. So our force being exerted by the horses combined is going to be equal to 500.0 newtons. We also know the velocity at 2.0 meters per second. We know the time is 10 minutes. Big red flag, we don't want time in 10 minutes. We'd like it in seconds. So we're going to multiply this by 60 seconds over 1 minute so that we can get 600 seconds for our time. So the first thing we want to do is find the work. We know that work equals force times distance. We also know that we don't know the distance these horses travel, but we can find it because we know that velocity equals the change in distance over the change in time. And when we plug values in for the velocity, we can get change in distance because we know the change in time is 600 seconds. Therefore, our change in distance equals 1,200 meters. We can then plug that into our equation there. We know the amount of force that we can put into our equation there, and we end up knowing that work is going to be equal to 6.0 times 10 to the 5th joules. The second part of this question asked us to find how much power. So I'm going to use a different color here. How much power is delivered? Well, we know our equation for power is work divided by change in time. We can simply plug our work in here. We know that time is 600 seconds. So when we do the math, that's pretty easy. It's 1.0 times 10 to the third, and that's watts. If we want to convert that to kilowatts, we can at this point. It's just simply 1.0 kilowatts. So there's our work, and there's our power. Here's a little problem you can try. See if you can get this on your own. Here's a student that's 50.0 kilograms. Actually, that student's probably a little bit more than 50 kilograms. The picture doesn't match, sorry. He climbs a 5.00 meter rope, constant speed. His power is 200.0 watts. How long does it take him to climb the rope, and how much work does he do? So pause the video, see if you can do this on your own, and then see if you get the right answer. So if your time that it took for the student to climb that was 12.3 seconds, and the work the student did was 2,450 joules, then you got it right. Let me show you just briefly how that works in case you didn't get it right. So to find the work, I would actually do the work first because once I find the work, it's easier to find the time. So work equals force through distance. I can substitute mg in for the force because the only force acting on this student that we've been told of is the force of gravity. We're not including friction or anything of that nature. So we're going to substitute mg in for the force of gravity. And the displacement is 5, and so I get for my work, when I multiply these together, 2,450 joules. In order to find how long it takes the student to do this, I'll use my power equation. Power equals work divided by time. I can plug the value in that I found for work, and I know the power is 200.0 watts, so I can plug that into the equation, and I can solve for my delta T. So looking for some advanced proficiency, a good idea might be to read in your textbook pages 190 to 191. That's talking about Einstein's special theory of relativity. It might be interesting. Take a few notes, look at some things of interest on there, highlight some key ideas, or write your own problems, or show multiple approaches to solving some of the problems, or any other ideas you come up with that go above and beyond the required work. And I look forward to seeing what you come up with, and we'll see you in class.